Hey everyone, welcome to ashatech.com, your engineering sciences channel. In this video, we are going to look at balancing of a rotating shaft, and we have got a guiding question. We must always know that a rotating shaft at one point, if it is not balanced, then there is going to be a problem that will result into vibrations and vibrations which can result into an easy failure of that shaft. So what we have to do, because of that unbalance, there is always a centrifugal force or inertia force that is set in once the shaft begins rotating. So to avoid the effects of the unbalanced force, we have to introduce what we call balancing. And this problem here that is in this question is going to address one of the ways of balancing by introducing a mass on the shaft to counteract the effect of the inertia force or the centrifugal force. So the question says, okay, after a long service, the bearings of a machine shaft worn out, causing the center of gravity of the shaft to be offset by 3 millimeters from the axis of rotation. The shaft is shown below with its bearings spaced 2 meters apart. If a total mass of 30 kilograms is mounted at a point 0.6 meters from bearing A to balance the shaft, determine the dynamic loads on the bearings when the shaft rotates at 600 revolutions per minute and the maximum and minimum loads on bearings. So this is the scenario that is set before us. We have a shaft that is rotating through bearings A and B. Then there is a mass that has been introduced, 30 kilograms, to balance or to counteract the effect of the centrifugal force that has been set out as a result of this shaft going out of balance, because we are seeing that the center of gravity of this shaft is being offset, or is going out of the radius of rotation by 0.3 millimeters. So the distance from where the mass is put is 0.6 meters from bearing A and 1.4 meters from bearing B. So let us look at the solution to this particular problem. Now, if they want dynamic loads, we have to note that when the shaft rotates, the dynamic loads are due to the reactions at the bearings as a result of the centrifugal force F. We know here, if the force, the mass is put here, there is a centrifugal force that is going to be generated as a result of this force. As a result of this mass. So if it is, for example, the shaft is rotating and this mass is moving upward, then it will experience reactions that are going downwards. That's why we have RA, then we have RB going downwards. If the mass is here during rotation, then it will experience the reactions at the bearings here will be upwards. So therefore, let us look at the centrifugal force. This centrifugal force, remember, is equal to mass times the square of angular velocity times r, which is the eccentricity or the distance between the center of gravity of the mass itself and the center or the axis of rotation. So since the distance has been given us to be 3 millimeters, then we can say that force is equal to 30 times 2 pi times 600 divided by 60. Remember, this omega is equal to 2 pi n out of 60. This is in radians per second. We are changing it to radians per second. Therefore, we have it as 2 pi out of 60 times that n, which is in revolutions per minute. Therefore, we will have 30 times 2 pi 600 out of 60, everything squared, times 3 out of 1000 to convert it to meters. which would give us 355.31 Newton. That is the force that comes as a result of centrifugal force acting on that mass. So now this force is the one that is responsible for the dynamic rods at the bearings. Therefore, if we consider the upward reactions due to the force F pointing downwards, we are considering a scenario when the shaft is rotating and this centrifugal force is pointing downwards, the reactions will be experienced upwards. So if we consider equilibrium, the reaction Ra plus Rb is equal to 355.31. That means upward forces are equal to downward force. Upward forces are equal to downward. Okay, then if we also take moments, sum of moments, we are saying sum of moments is equal to 0 about A. So if we take moments about A, Rb times 2, we see Rb will be acting in anti-clockwise direction, whereas this force due to centrifugal force, the centrifugal force will be acting in a clockwise direction. Therefore, Rb times 2 is equal to 355.31 times 0.6. Then Rb will be equaling to 106.59 newtons. If we use the sum of upward forces equal to the sum of downward forces, then we can say Ra is equal to 355.31 minus 106.59. Then we shall have Ra as 248.72 newtons. Therefore, the dynamic rods at A and B are 248.72 newtons and 106.5 newtons respectively. So those are the dynamic rods that are experienced at the bearings A and B. So let us proceed and look at the maximum and minimum loads. So we must note that when the shaft rotates, the lines of action of the dead weight mg and the centrifugal force F coincide. In other words, if the shaft is rotating, there is a point where the dead weight and the centrifugal force are pointing in the same direction, and there is a point where the dead weight and the centrifugal force are pointing in the opposite directions. Therefore, it means at a point where both are pointing in the same direction, we will experience the bearings will experience the maximum load, and where they are pointing in different directions, in opposite directions, then the bearings will experience the minimum loads. So let us consider the reactions at A and B due to the dead weight. If we only consider the static conditions of this shaft, then when there is no rotation, there is this mass existing. So if it is existing, we will still say sum of upward forces is equal to sum of downward forces, and therefore Ra prime plus Rb prime is equal to 30 times 9.81. This is mg, mass times acceleration due to gravity, and this gives us the total of these forces. Okay, then if we also take moments, sum of moments about A will also give us 0. So meaning that 294.3, this weight is acting in a clockwise direction, times 0.6 from A is equal to Rb. Rb prime is here, so it will remove a distance of 2. If the perpendicular distance from B to A is 2. So I mean Rb prime will equal to 88.29 newtons, and it is going to be acting upward. So if we use the equation obtained above, Ra prime plus Rb prime is equal to 294.3 newtons, then we can get Ra prime, which is 6.01 newtons, also acting upwards. So the maximum load on bearing A will therefore equals 206.01, which is due to the mass or the weight of the load, which is 30 kilograms. Then we will also have the force due to what? Due to the dynamic load, which is 248.72. So this will equal to 454.73 newtons, and this is the maximum load the bearing at A will experience when there is rotation. Then the minimum load on bearing A again will be 206.01 minus. Remember, this force is acting upwards. This force is acting downwards. The 206 is acting, of course, this is this is acting upwards, but this force is acting downwards, meaning that if I take 206.01 minus 248.72, I will have negative 42.71, and this will be experienced downwards. What about if I go ahead and look at the maximum load on bearing B? So on bearing B, I have the force due to centrifugal force, which is this one. Then I have also the force due to the weight of the mass that has been put in between the two bearings on the shaft, and this would give us 194.88 newtons. Then if I'm looking for the minimum load on bearing B, it will be 88.29 minus 106.59, which gives us negative 18.3 newtons, and this force is acting vertically downward. We can check this force is here 88 for RB is acting upwards. So if we take away the force due to the centrifugal force at the dynamic load, these dynamic load are forces, of course, that we are looking at, for example, to determine the minimum and maximum load, since they are also part of the system during rotation. Then the minimum load at the bearing B will be 88.29 minus 106.59, and this will be, as we have said, this will be acting vertically downward. So thank you so much for watching. See you in the next video.